Okay, today I'm going to talk about 6.3 shell method. Shell method is another way that we can find the volumes of solids through revolution. It's going to be easier to use this method in certain such situations, which I'll explain here. Here we're going to find the volume of the solid formed by revolving the region bounded by this parabola here and the x-axis. Now this certainly isn't something I should need a calculator for. In this context, it's not like you have to have all the details. There's just a couple important ones. The most important thing, since we're talking about the x-axis, is going to be where it crosses the x-axis, so we're talking about the zeros here. So I'm interested when this thing is equal to 0. Factor a negative out. And this thing factors. So our two intersects, x-intersects are x equals 1 and x equals 5. So like I said, the details here, it doesn't have to be a glorious graph. It just has to have the most important things, which 1, 2, 3, 4, 5 are those x-intercepts. Okay. Doesn't matter what the y value is for the vertex or anything like that. But we do know it's going to be equidistant, so it will happen at 3. Okay. So anyways, this is our function. So what we're talking about here, it's bound by the function and the x-axis. Our region is this region here. Okay. Now what we're going to do to generate our shape is we're going to rotate this about the y-axis. Now, we did this in the last section using, in this case, since it would certainly have a hole, would be a washer method. But whenever we rotate around a vertical line, if you remember, we had to write it in terms of y. This would be extremely problematic because this isn't a function of y, it's a function of x. It passes a vertical line test, but it's not a function of y. It doesn't pass a horizontal line test. We could do it, but we would basically have to define this in two separate functions. It would be quite complicated compared to using the shell method here. Okay, so first of all, just like before, if you can visualize these things, that's great. If you can't, it really isn't a big deal. I'm going to do my best to sort of draw these things, but you know, I'm not necessarily an artist here. So we're rotating this thing about the y-axis. So what we're getting here, let's continue this on. Okay. Okay, so what we're getting is this thing is replicating, and oof, it's a little rough. Anyways, if you imagine rotating this region around, okay, from this side it's going to be completely solid. Okay, it kind of is like a donut, that like half a donut or a half a bagel that we cut in half. Okay, to put some cream cheese on it. Okay, so this is the shape we're talking about. Now, when we do a disc or washer method, we're always going to cut that perpendicular to whatever the axis of rotation is. So when we cut that perpendicular, if we were going to do it that way, we'd have to write as a function of y. So what shell method allows me to do, instead of cutting this into discs and washers, I'm going to cut this perpendicular to the x-axis, okay, which will allow me to keep in terms of x. So what I'm basically doing, and like I said, you know, if you can visualize these things, great. If you can't, so at any given point, I'm going to cut this thing, and it's going to go all the way around. It gives us basically a cylindrical shell, okay? So we're going to take this thing, and this is going to go all the way around. So in other words, we're going to place one shell on top of the other, okay, creating the entire shape. And just like we do in typical calculus fashion, there's going to be an infinite number of these things. They're all going to have a thickness of dx. So that part of it is pretty much consistent with what we talked about. If you imagine like pieces of paper, we're sort of stacking these shells together. If you've ever seen these Russian dolls where the shapes are exactly the same, but one's stacked inside of another, it's kind of like that. Each shell will be a different shape. So the ones here are going to be quite small. The ones sort of right there are larger, and then we're going to go throughout. So we're going to cut this thing into all these shells. Let's take one out and put it down in front of you. So the shell here, okay, so what I have in blue is a cylinder, okay, hollow cylinder, because there's other shells inside of it with a thickness of dx. Okay, so this is what I'm showing right here. Okay, so now what I'm going to do is I'm going to cut that thing and spread it out in front of you. And now, just like if we were talking about a washer, I want to find the volume of that one shape, so I then can add them all up through integration to get the volume of the entire thing. Okay, so if I cut this thing and slice it, clearly what I'm going to have is basically a very, 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 very thin rectangular prism. The height of that rectangular prism will be dx, right? So I need the area of the base, just like it was a disc or a washer, and I'm going to multiply it by the height. Okay, so the height here comes from right here. The height here is just going to be our function, right? So wherever I cut this thing, that height is going to be the function, which is y equals negative x squared plus 6x minus 5. So that's the height here. The length, or whatever you want to call it, realize that this is the circumference of this thing. So circumference is 2 pi r. Now what's the r going to be? Well, the r is going to be whatever the x is, okay? So that the circumference of this will be 2 pi x. Okay, so the volume of one of these cylinders is going to be 2 pi x, and then times the height, negative x squared plus 6x minus 5, and then we're going to multiply by dx. So that will give us one of the volumes of these cylindrical shells. Now what we want to do is we want to add them all up. So understand what's going to happen here. Sometimes people get confused because they think we have to do something over here. Keep in mind that as I slice this thing up, I'm actually getting the entire shape with just going from 1 to 5, because I will get all of those shells which will form that area over there, or region over there, I should say. So all I'm going to do here is I'm going to integrate this thing from 1 to 5, from 1 to 5 here. Don't forget the 2 pi. Typically write the 2 pi out in front. Very common error, whenever we do the disk or shell methods, we always have that pi out front. When we do shell method, we have 2 pi. People sometimes do make the mistake of switching those. Keep in mind why we have 2 pi. It's because we're getting that length there from circumference, where if I do a disk, it's pi r squared. It's not 2 pi r squared. So it's important to keep that in mind. Now, these types of things, we could do this by hand. It would be quite obnoxious. As I said earlier, in 6.1, I wanted you practice using the fundamental theory of calculus. In 6.2 and 6.3, I really just want you to focus on setting these things up, and then we can just use Math 9 values. So I just plug this in my calculator. I get 201.0619, and that is the volume of the region defined here. Okay. So let's talk about this in a general way. Okay, before we get to a general formula for shell method, I wanted to actually look at some other examples. We're basically using, well, not basically, we are using the same region that we talked about in the first example. So this region here formed by the parabola and the x-axis. But instead of rotating around the y-axis, we're going to rotate it around other vertical lines and see what happens here. So I'm going to go ahead and start off. I'm going to do 2 of these. X equals -2. Okay. So that vertical line, I'm going to rotate about that line. Now, our general shape is the same. It's just going to get, and I'm not going to do this to scale or anything like this. That should be equidistant. Doesn't really look equidistant, but that's okay. So we're going to rotate that around the line x equals -2. The shell, the shape is generally the same. What's happening here is the hole's getting larger. So sometimes people think, oh, well, the volume's going to be the same because this, realize that now we're getting a lot larger shape. So the volume's definitely going to increase here. So don't make the mistake of thinking the volume's going to be the same. Sometimes people intuitively think through these things wrong. You want to rely on the calculus and not go with what intuitively seems correct. So let's see what happens. So once again, I'm going to rotate this thing around. Okay, I'm going to cut this into a shell. Actually, an infinite number of shells. So let's take a look at one of these shells. Let's cut that thing out. Let's put this up now. Let's put it down here. Okay, so let's take this shell here and see how changing the axis of rotation changes the shell. Okay, so once again, the thickness here is an infinitesimally small change in x, or dx. The height of the shell, I want to point out, doesn't change. The height of the shell here is still going to be this function, negative x squared plus 6x minus 5. The length of this shell is still going to be the circumference, but notice what's happening is the r is increasing. Okay? Now the way I figure out what this r is, I'm always going to take whatever x is, and I'm going to subtract whatever's on the left. And when you see x equals 5, that's going to be the reverse. So x minus negative 2, so that's going to be x plus 2 is going to be my r. So that's going to be 2 pi, and then, oops, not r, 2 pi, and then our r is x plus 2. X minus negative 2, which gives us x plus 2. So if you think about where our x is, we're really just adding 2. So the minus the negative 2 takes care of that and adds the 2 for us. So we don't really have to think too much about it. Basically, just like when I do like discs and washers, something above minus something below, I don't have to worry about where the axis is. Same thing with shells in those radius. It's always going to be whatever's on the right minus whatever's on the left. So this will be 2 pi, and that is our r. Now from here, it's going to be the same as what we had before. So this one here, it's going to be 2 pi r. Okay, and then our height, negative x squared plus 6x minus 5 dx. And then to get all of them, we're going to integrate from 1 to 5. Notice, nothing's changing here other than this right here. Now, if you ever get confused, think about this, because sometimes people want to do different things with the limits because we change our axis of rotation. Realize that 1 is going to give us that first shape. This is our r, and notice our first r is 3. The last r, if I plug 5 in, notice it's going to be 7. That checks out. So if you ever get confused, try your first value, plug it in your r, take your top value and plug in an r, and see that it is indeed generating those different radius. Okay, so that is part A. Part A, I am getting, like I said before, let's just focus on setting these things up. We can go ahead and plug this in our calculator for the time being. Also, when these are a closed calculator on the AP test, they typically just have you do the setups. You don't have to, and they do end up being closed calculators. That's why it's important to be able to graph things like this without your calculator. However, quite often it's just going to be the setup and not the actual value. Okay, you can see, I mean, we could certainly integrate this, but dealing with these numbers here, it's going to be quite annoying. Okay, so let me set this up again, and then we'll do the rotation about x equals 5. This time we're going to take the same region, and we're going to rotate it around x equals 5. So this is going to kind of move off in this direction. Okay, so this thing spins all the way around. So what changes here is because we're rotating around that far boundary, we're not going to get a hole here. Now, it's not something I have to worry too much about. The calculus will take care of it if I just sort of think through it the same way. So once again, let's think about what's going to happen. So this thing's going to spin around here. If we cut it into cylindrical shells, let's take out one of those shells and take a look at this thing. So let's put this down right in front of us and then cut it out. Okay. And let's think about what's going to change here. And you can see once again that the height is going to be exactly the same. That height of that shell isn't changing no matter how I'm changing that axis of rotation. The height of that shell continues to be y equals negative x squared plus 6x minus 5. Okay. What changes in each case is the circumference because the r is changing. Now, same thing as before, 2 pi and then r. This time the axis of rotation is on the right. So it's now going to be 5 minus x, right? So 5 minus x is going to give us that r. Now, once again, if you ever get confused, let's set this up. So exactly the same way. So this will be 2 pi r, 5 minus x, the height of our shell, negative x squared plus 6x minus 5 dx, okay? And we're integrating that from 1 to 5, which is going to add up all those. If you get confused again, let's just see that this works out. Think of that far left boundary. If I plug 1 into that, what do I get for my r? I get 4, and you can see that that does work. My radius is 4. And if I plug 5 into this, you'll see that that's when we're right there in the center. The radius is actually 0. But I don't have to worry about that. The calculus will take care of that fact. Okay? So once again, setups are all I care about here today. So now I plug this in my calculator. I get 134.0412. Hopefully these are correct. I did these earlier. As you know, sometimes I make mistakes. If I make a mistake, bring it to my attention in class so we can talk about it. Okay, so let's generalize this thing here. All right. So the way this is going to work is just like when we do discs and washers, we're going to have a set formula here, okay? And basically the formula is as follows. So this is our shell method. Now these things will change, but generally speaking, it will always be 2 pi out front. I encourage you to sort of think through that. As I said, the 2 pi comes from the fact that 2 pi r is circumference. Memorization can be tricky. We're going to integrate from a to b. You're always going to do the radius here. Now what you saw with this problem was the radius changed depending on where we were. Wherever the axis of rotation was, what changed was the radius. And I didn't give myself enough room here. Let's move this over. Okay, so 2 pi a to b, and this will be the radius, which changes as we change the axis of rotation, and the height of the shell. Now in this particular case, the height of the shell just ended up being what the function is. We'll see different cases where we're defining the height of the shell based on multiple functions. But typically, as I change the axis of rotation, the height doesn't change. If you think about it this way, when we do the disc or washer method, as I change the axis of rotation, the horizontal axis of rotation, what's going to change there is the r's as well. So the r is always changing in both methods. And then if we're talking about a function of x, we're going to do dx. If we're talking about a function of y, we do dy. So that is my shell method. Okay, let's take a look at a couple more examples here. Okay, this time we're going to do a function of y. And by the way, I don't want to write all these words. I'm talking about the region that is bounded by the function of y, x equals 4 minus y squared, the y-axis, and I'm talking in the first quadrant, and I want to rotate that about the x-axis. One thing about functions of y, and I talked about this last year, they can be tricky for folks. It's like trying to write with your left hand. Really intuitively, it's exactly the same as a function of x. It's just that your input is now your y's, your vertical values, and your output are now your x's, your horizontal values. If you ever get confused, like if I want to sketch the graph of this, and I'm having a hard time doing that, I always go to this table here. I think it helps if you get confused. So think input, output, okay? And if we're doing a function of x versus a function of y. I probably should use different notation here because these aren't necessarily going to be the same. So we'll call it g of x, just function of x versus the function of y. So function of x, the input are the x values, which least to greatest run left to right. Okay. The output, of course, are the y values, the vertical, which least least to greatest run down to up. Now this helps, especially if I'm getting turned around and getting confused what I'm going to do, and it helps in other cases too. Function of y just flips those. So the input is now down to up, least to greatest, and the output is now left to right. Okay, now how can I use this? Well, this equation here, we understand what that looks like as a function of x. So let me just sketch that real quick. As a function of x, it looks like this is a function of x. Okay, so this is not this function. If you draw this graph for that function, you're not going to get it right. Okay, or I'm going to dot points anyways. So realize that what we're talking about here is the exact same thing, except think about this. This is a parabola that opens down. Okay, so it opens down. So if I look at a function of x that opens down, and this is how you use it, this is going to open to the left. So this thing is going to open in that direction. Okay, and the next thing is, so normally this thing is on the up part, 4, right, the y-axis. This will be on the right part. Or if you think about it this way, my y-intercept is 0, 4, which means I'll get an x-intercept of 4, 0. So instead of up, it's right. Instead of opening down, it opens to the left. Instead of x-intercepts of -2 and 2, it's y-intercepts of -2 and 2. Okay, now actually let's pay attention to the rest of this. We only care about the first quadrant, so we're talking about this region in here. Okay, let's get rid of this because this is not the graph I'm talking about. So what I'm going to do now is we're rotating this about the x-axis. Now, of course, if I'm talking about functions, and I'm going to formalize this towards the end of the video here, but so let's recap. If when I'm doing functions of x and I rotate around horizontal lines, functions of x around horizontal axes, I'm going to use a disk or a washer method. Okay. If I take a function of x around vertical axes, okay, I'm going to use the shell method. So functions of y flip that. Okay. So normally horizontal, right, function of x, that's going to be a disk or washer. In this case, it's going to be a shell because it's a function of y. Okay, so let's think about what's going to happen here. So if you want to give it a little sketch, kind of almost looks like a cap to a plane or something like that. So what we're going to do is we're cutting it perpendicular to the y-axis. So these are going to be my shells. Hopefully this isn't looking too confusing. So now it's going to be, if you remember from before, it's going to be radius times the height of the shell. And it's going to be dy instead of dx. A to B, and then we have the 2 pi out front. So that's going to be our general formula. Our job is to figure out what the radius is, what the height is. So if you remember from the examples before, the radius were always right to left, right? So if I'm normally doing a radius as right to left as a function of x, as a function of y, it'll be down to up. So in this case, our function, our height, is going to be this function, which is going to be 4 minus y squared. So that's going to be right. Okay. Now the radius, normally when I do the radius, right, it's right to left. Now this is going to be down to up. So what's my radius going to be? It's going to be y. And now instead of going with my limits from 0 to 4, right, I'm going to go 0 to 2, and that's going to be a 2 pi. And that's how I'm going to do a function of y here. And let's see if I calculated this. I actually didn't calculate this one. I want to remind you when you do functions of y and I plug this in my calculator, it doesn't change anything. You just put x's in. The calculator doesn't know the difference. It's the value we're interested in. Okay, now let's kind of put this together because quite often they don't tell you what's going to be the best method. If they do say use shell method or use disk and washer, then you know that you're going to have to do that. But in general, you want to use whatever method is best. So let's talk about that. Okay, for this last example here, we are going to take our region, and we're going to rotate it about all sorts of axes, both vertical and horizontal. It's important to sort of keep this straight. Once you sort of wrap your brain around it, it's not too bad. Now mind you, I'm talking about a function of x here. So if we rotate a function of x around a horizontal line, like the x-axis or y equals 3 or something like that, we're going to use the washer method if it has a hole in the cross-section, or we're going to use the disk method if it doesn't have a hole, okay? If we rotate our function of x around a vertical axis, it's going to be the shell method, okay? If we do a function of y, of course it just flips. Function of y around a horizontal axis will be shell. Function of y around a vertical axis will be a disk or a washer method. All right, so here's our region here. Our region is formed by the function f of x, y equals 2, that horizontal line, and x equals 1, okay? So we have this region right here. So x-axis, that's pretty basic. That is our washer. And I'm just going to do the setups here. If you want to calculate them for practice, feel free. But I think it's a little bit overkill at this point. Okay, so around the x-axis, we're going to have that's horizontal, so that's going to be a washer. Pi out front, we're integrating from 0 to 1. Okay, big R, when I'm doing the washer, always go with the function that's farthest away, and then always go with whatever's on top minus whatever's on bottom. So we'll go with the function farthest away, which is f of x. We have to conserve room here. Let's call this f, okay, minus, oh, not minus because we are just rotating about the x-axis, so call that f squared x minus, and then our other function is the constant function 2, so that'll be 2 squared dx. If you want to call that 4, you can. It really isn't necessary. It is up to you. Okay, so the y-axis, this is going to be a vertical line, so that's going to be our shell method. So that's going to be 2 pi, okay, 0 to 1. Notice the limits aren't changing. In fact, the limits don't change for any of these. The height of our shell, now the height of our shell is actually, because we're going to have to do both of these functions, the height of our shell, well, let's talk about our radius. What's the radius? The radius is going to be x. Okay, so if our region's on the right and we're rotating around the y-axis, the radius is just going to be x. What's the height of that shell? It's going to be function above minus function below, so this will be f of x minus 2 dx. Okay, so that's the y-axis. And like I said, if I make an error, please point it out to me when we get to class. Y equals -2. Once again, that's a horizontal line. Since it's below, I'm going to go regions minus the axis. So pi, 0 to 1. The big R, function farthest away, that is f of x, minus -1. So that's going to be plus 1 squared, so f plus 1, minus, and then our little r is going to be 2 minus 1, or excuse me, 2 minus -1, so that'll be plus 1 squared dx. No need to simplify these things. In fact, I kind of like them left like this because it's clear what's happening. And that is rotate around y equals -1. Okay, x equals 3. We're back to a vertical line, so we're back to shell. So that'll be 2 pi, 0 to 1. That isn't changing. The height is going to be the same as it was here. So the height is still going to be f minus 2 dx. What's going to change is the radius. So since the radius, since the axis is on the right, it's right minus our region, so this will be 3 minus x. And if you need to, plug in the values and test it out, okay? And then if we rotate around y equals 3, okay, so we're back to a disk or washer method. So pi, okay, 0 to 1, big R. Now the axis is on the top. Let's get rid of this. This is from before. So we're going to go axis minus function. Always go with the one farthest away. So when the axis was below, f always defined the radius that was farthest away. Now the axis is above, it's going to be the 2. So this is going to be 3 minus 2 squared. That's our big R. Our little r will be 3 minus f squared. dx. So that's around y equals 3. Okay, and then x equals -1. We're back to shell method. 2 pi, 0 to 1. The height, it's going to stay the same. It's going to be f minus 2 dx. And then the radius, whatever's on right minus whatever's on left. So the region is on the right, so that's going to be x, and then minus -1, so that'll be x plus 1. And that is shell method. Okay. So, you know, I think I threw a lot at you here. When we practice these, you're going to find that this makes a lot more sense once we sort of kind of clear this up. So that's 6.3 shell method.